We are now recording, so let's get going to the current slide. And before we get going there, let's talk a little bit about some announcements. First, you've heard these. I'll just go through these quickly. Always looking for good people in math, which is you guys, to be on the math team. They meet every Friday at noon and on Mondays at 3. And on the Birmingham West campus, the science building, which is the C Hall, and in room C100. Mr. Rossi is the coach, and they've been having a great time and learning a lot of math. They're having a great time. That's the main thing. It's just learning the math is the bonus. Okay. Tutoring. We have 2 places you can get tutoring here. Or you can do tutoring here. You are some of our best students, so you could easily be a tutor either for student support services down the hall from here or the Space Center downstairs from there. Okay, and so that's tutoring opportunities. I forgot to make this announcement at the beginning of my last class, and actually some students reminded me on the way out. You know what's happening Thursday? Okay, Honors and Awards Day. And I think it starts at 10. Yeah. Okay, which means we have to be there, meaning the faculty have to be there probably by 9:30 or 9:45, which means that my first class is going to be much shortened, and this class, unfortunately, will probably not meet at all, because I'll be gone before this class begins. The ceremony will take at least an hour, more likely close to 2, and so it wipes out our whole class period. So there is no class on Thursday for this class. Do you want to try to make that up or just absorb it? I mean, we don't have to, because it's not something that's happening to me. It's a school function. What's your feelings on it? You want to just cover more trig? And we could add 15 minutes, 30 minutes to the next several classes and make up the time, or just call it. Get as much as we can. What's your thoughts or feelings? You paid for the whole course. You want your money's worth, or are you happy with just what we can squeeze in? Tell me. I can go either way. Huh? Okay. Without doing any extra. Okay, we can go that route too. Okay. Now, was there anything else? Seems like there was, but I can't think of it now. Oh, yeah, one more thing. I don't know what normally on Friday is anymore, because the month of February, I don't think I was in the office more than 1 or 2 Fridays, and that continued that way almost most of the month of March. And now April, last Friday I had to go to meetings down in near Montgomery, and this Friday I've got another infusion. Okay, so far in April, 0 for 2 on Friday. So, but hopefully next Friday, not this Friday, but the following Friday, I'll be on campus again. So I will not be on campus at all this Friday. I've got an infusion. I have to be there, I think it's 7, unless I have to do labs when I have to be there at 6. Okay, so there's no way I'll be on campus Friday at all, because the infusion takes most of a day, and after it, I'm not really supposed to drive very far, so I just drive home and go to bed. Okay, so I'll play with the dog a little bit maybe if I feel like it. Okay, but I'm not supposed to be driving, so I won't be going to Birmingham campus. All right, any questions before we get started today? All right. Now, last time we talked about the half-angle formula, but we didn't have a chance to do an example with it. Does anyone remember what the half-angle formula said, what it looked like, anything such as that? There's actually 3 of them we typically use. What are they? It was a long time, 5 days at least, you know. Okay. Oh, I'm sorry, I forgot to get my pen set up. Okay? Sine of u over 2 would equal plus or minus the square root of 1 minus cosine u over 2. And whereas cosine of u over 2 looks very similar, except it's the square root of 1 plus cosine u over 2. And tangent of u over 2 is different, as it is always, okay, in that there's no pluses or minuses involved. It's just this formula, and you can write it in two different forms. 1 minus cosine u over sine u, but that's the same as sine u over 1 plus cosine u. Okay. So yeah, there are 3 half-angle formulas. So what? What's the big deal? Well, they say find the exact value of the sine of 105 degrees. Wait a minute! That's not one of our favorite angles. We like 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, and then multiples of that, which would be over here, that would be 120 degrees, 135 degrees. Hey, 105 isn't in that. We don't like those numbers. We like our favorite ones, okay? But they say find an exact value of it. What can we do? What were some of the others? I said 90, what did I say? Yeah, 120, 135, 150, 180. Those are all nice ones. 210, 235, no, 25, yeah. So yeah, all those, okay? I just said something that should be useful. Huh? 105 is exactly half of 210. So sure enough, we can use the half-angle formula here. So let's let, in this case, u, according here, let u equal 210 degrees. Then u over 2 is equal to what? 105. And they're looking for sine, so the sine of 105, which is u over 2, is equal to plus or minus the square root of 1 minus cosine of, and what was u? 210. And I think we can figure that one out, divided by 2. Except for a problem we have here, Houston. Why do we have this plus or minus here? Because we took a square root back a long time ago, okay? Well, this is going to give us 2 answers, isn't it? That's not good, not for a function. So what do we do? Sine of 105. Where are you, Waldo? Second quadrant. What's the sign in the second quadrant? Positive. So forget about the minus there. It's just going to be the square root. So we don't need to haul that around anymore. Okay? So now we can plug and chug. So the sine of 105 is equal to the square root of 1 minus, and what is the cosine of 210? Now with 210, where are you? Third quadrant, okay? And what's your reference angle in that? Okay, cosine of 210 is going to be plus or minus. Minus, because tangent is what's positive in the third quadrant. So it's going to be a minus, and 210, what is the reference angle for 210? Here's 180, there's 210. What's the difference there? $180 to 210. What's the difference there? Second? 30. So that would be the same as 1 minus the negative of cosine 30. So we're just going to put it plus cosine 30. And what is cosine 30, by the way? That's one of our favorites. What is it? You're going to say it? Second? Okay, 30 degrees is pi 6, yes. What is the cosine of that? One of our favorites. Second? Okay, that sounds like an angle to me. We know the angle. It's either 210 or, 30 degrees or pi 6. That's the angle. What's the cosine of that angle? Generally, you don't have pi's in that. You could, I guess, but pi usually represents a radian measure. So I need a number. Second? That's the sine of 30 is 1/2. Square root, second? Square root of 3 over 2. So that would be plus the square root of 3 over 2 all over 2. Okay? Now that's what we sometimes call, I call a complicated fraction. Some texts will call it complex fractions. I really don't like that. What I'm going to do to that, and this is all under the square root, remember, I'm going to multiply numerator and denominator by the least common denominator, which is 2. Okay? And that will give me, and this is all under the square root, that will be 2 plus root 3 over 4. Right? Get out of there. Okay. Well, I can break that down as the square root of 2 plus root 3 divided by square root of 4 is 2. Now that's one way to express it. You could do others. I think that's the simplest way. Let's see if that's what they do. Yeah. Okay. So let me clear this out of the way unless y'all are still writing. Any of you still writing? Okay. Okay, we'll erase all that. And let's see what they do. Begin by noting that 105, even though it's not one of our favorite angles, it is exactly half of one of our favorite angles, or a multiple of that. And that is half of 210, and 210 has a reference angle of 30, and 30 is one of our favorite angles, 30 degrees. So, using the half angle formula for side, and the fact that 105 lies in the second quadrant, so we're going to use the positive value of that square root. So sine of 105 will be the square root of 1 minus cosine 210 divided by 2. And they went right to the, now let's go back and see this. So you have a minus there. Cosine of 210 is negative, okay? So the minus times minus will make it plus. And the cosine of 210, that has the same reference angle. That's the same, the reference angle for 210 is 30. Cosine of 30 is square root of 3 over 2. And then you divide that by 2. And then they magically go to this other thing without telling you how they did that. But I showed you how one way to do that is square root of 2 plus square root of 3, all under the radical, divided by 2, which is not under the radical. The positive square root is chosen because sine of 105, that's what we're looking for, is positive because it's in quadrant 2, and sine is always positive in quadrant 2. So there's a place where you could use the half angle formula and know exactly what the value is. But I look at that, that doesn't help me a lot because I don't know what square root of 2 plus the square root of 3 is. That's a messy thing in itself. So you're going to have to use a calculator to get that. So why don't you just use a calculator to get sine of 105? Okay. Now, later in calculus, you will, on rare occasions, need to know that half-angle formula. But it's not anything I would suggest you memorize. Just when you need it, look it up. Okay. There is a checkpoint. I would definitely do the checkpoint and see what you get there. That happens to be find the exact value of cosine 105. Couple little differences there. I'll let you work with those. So let's see. They're skipping example 6. So let's us do example 6. Find all the solutions of 1 plus cosine squared x equal 2 cosine squared x over 2. Now, time out, they said find all the solutions. That indicates this is not an identity. This is an equation that we're wanting to find the solutions for. An identity, they would be true no matter what the x was. This is not the case. We're looking for the values of x which make that true. Oh. On the interval 0 to 2 pi. So it's not an infinite number of them. It's some finite number of solutions for x which make that true. How would you begin that problem? What's a little messy about it? Yeah, the x over 2. So let's leave the left-hand side alone for now. We'll come back for that later, but don't lose it or forget it. 1 plus cosine squared x supposedly is equal to 2. Now, we need to put in the cosine of x over 2 from our half-angle formula, but then we're going to square it, so guess what that means? We're going to lose the radical. Okay? So what is the cosine of x over x divided by 2? You just gave it to me a little while ago. I know it was 15, 20 minutes. It's a long time. Okay. Or maybe I gave it to you. No, I think y'all gave it to me. Okay, wait. Not the cold, though. This is just a sneeze. Excuse me. Poor people living at home, listening at home. That's going to mess them up, isn't it? Never mind. All right. Cosine x over 2. What is that? Hint, it starts with a plus or minus. Remember? The square root of 1 plus x. It was u because it's u over 2, but now it's over 2. But you're squaring that, right? Now squaring it does two really nice things for you. Bless you too. Okay? Number one, whether it's plus or minus, when you square it, it's going to be positive, right? And number two, when you square a square root, you lose the square root. Okay? So I wrote it out that way so you could see that. This will now become 1 plus cosine squared x is equal to 2 times, lose the plus or minus, lose the radical, lose the square. 1 plus cosine x over 2. Now, what's the nice, handy, convenient thing you see happens next? The 2's divide away and become 2 over 2 is 1. So now we have 1 plus cosine squared x is equal to 1 plus
cosine x. Okay. We want to find all the values for x's in the interval 0 to 2 pi, which make that true. So what do you do? Okay, it's a quadratic equation in cosine. Yes, bring everything to the left, so we get everything on one side, 0 on the other, because quadratics, you like to have them set up that way, right? So what will we do? Subtract 1 from both sides, and subtract cosine x from both sides. Okay, guess what happens to the 1's? They all disappear on both sides. And then you have cosine squared x minus cosine x is equal to, and these disappear too, leaving you nothing. Okay, 0. Now what do you do?
Take out cosine x?
Yes, factor out a cosine x. I thought he was taking it out for dinner, but whatever, okay. So let's factor out a cosine x. And what does that leave you with? Cosine x minus 1. And that is equal to 0. Now that gives you a product of two entities multiplied together gives you 0. So what does that mean for you? Either I'm going to go up here somewhere. Cosine x is equal to 0, or cosine x minus 1 is equal to 0. Anytime you have two or more entities multiplied together equaling 0, you know that one or more, or all maybe, have to be 0. So that's what that says for you. All right, let's solve that first equation. Where on the interval from 0 to 2 pi is cosine x equal to 0? Say again? I don't think so. Sine is 0 at 0. Cosine is 1 at 0. So where is cosine? At what? Pi halves and 3 halves pi. And between 0 and 2 pi, that's all we got. So this would be either x equal pi halves or 3 halves pi. Now, every half pi from there on, in both directions, is 0, but between 0 and 2 pi, that's all. Okay, now, the second equation, we need to do one little thing too, and what's that? What's that? Add 1 to both sides, and that gives us cosine x, as add to 0, is equal to 1. And where is cosine x equal 1? Whoops, I already told you, didn't I? Where is it? 0. At 0. Okay, so x equals 0. Is cosine equal to 1 anywhere else on that interval? It goes to -1, back to 0 at 3 halves pi, and back to 1 at 2 pi, but 2 pi is not included. That's a parenthesis there. 0 is included, so we got that one. 2 pi, you missed it by that much. It didn't quite make it in. So these are the three values: x equals 0, x equal pi halves, and x equal 3 halves pi. And they do show you a little graphical solution that you could have done on your graphing calculator if you had it. That's exactly the three answers they get: x equal pi halves, 3 halves pi, and x equals 0, just like we did. There is a checkpoint there, which would be pretty good to do as well. All right, any questions on those?
All right, let's move on to product to sum and sum to product formulas. We'll show them both. As we get more and more of these, they get less and less practical uses. I think, there are some, okay, I don't want to diminish them. There are some very practical uses, but not nearly as much as for double angle formulas and even a little bit half angle formulas. There are sometimes in calculus where you do need to know this. But you usually find other ways to do those as well. Each of the following product to sum formulas can be verified using the sum and difference formulas. Okay? You know what this is, cosine of u minus v, right? Cosine u, cosine v, plus sine u, sine v. Subtract from that cosine u plus v, which is cosine u, cosine v, minus cosine u, sine v. And you notice this was a cosine u, cosine v, and this was a minus cosine u, cosine v. They just go away. But the signs, this was a plus, this was a minus, so minus and minus make plus. So two of these make this, take half of it, and you got this. So this is just a rewriting of your sum and difference formulas for cosine. And that gives you the product of sine u, sine v. Those products show up in the sum and the difference of cosine, sum and the difference of your cosine functions. Arrange them properly, and that's how you get this. Same thing here, this comes from the same two functions, but this time you're adding those two. You add the cosine u, cosine v, subtract. This is the minus sine u, sine v, this is the plus sine u, sine v, so when you add those, that disappears and that leaves you cosine. Okay. This comes from the sine 2v, times sine u plus v, and cosine u plus v. That both show up there, so that's what shows up here. Okay? And the cosine u sine v is the second half of that, so that's the difference between these two. So yeah, these are nothing new. They are the types of things that we had already, but we're just solving them for one piece of it. These product to sum formulas are used in calculus a little bit to solve problems involving the products of sines and cosines of two different angles. Okay? As in when you're integrating a product of sine and cosine that are not the same two angles. And there are rare circumstances when you do that. But they do exist, so yeah. These are nice to know, but guess what? You can find some table somewhere that has shows them and look them up. Okay? You don't have to go back and derive them. Though they're easy to derive, but they're that. So let's see, are they going to show example 7? Yeah, here we go. Rewrite the product cosine 5x sine 4x as a sum or a difference. So cosine 5x sine 4x, okay, as a sum or a difference, okay? Now, which was that? That was represented by the last one we just showed, right? In the block above the example. It's the last one, cosine u sine v. What does it tell you it is? 1/2 what? Say again? Sine of 5x plus 4x minus the sine of 5x minus 4x. Probably I should be putting those in parentheses. I did the first one, didn't get the second one done properly. Okay. All right, which is 1/2 of minus sine of x. Okay? That's all it asks for. Rewrite the product as a sum or a difference. There it is. Really wanted to be picky about it, you could say 1/2 sine 9x minus 1/2 sine x. That's a pure thing. You know, distribute that. But there's no real reason to do that, I don't think. Oh, yes, they do it. Sorry. They distribute that in 1/2 sine 9x minus 1/2 sine x. Okay. Now that's purely a sum or a difference. In this case, a difference. Okay. So, no big deal. Okay. Now, I wish doing this would show more insight. They show exactly the same thing I did, I think. Let's just see. Using the appropriate product to sum formula, you obtain that cosine 5x sine 4x is 1/2 of sine of 5x plus 4x minus sine of 5x minus 4x, which would be 1/2, and they just jump right to the thing. 1/2 sine 9x minus 1/2 sine x. Now, all the examples I think they show, maybe even the ones in the book, they always put the bigger number first. So when you do your subtraction, it comes out a positive thing here, sine x. But what if they had been reversed? What if this had been cosine 4x sine 5x? Well, two things you could do. You could just flip them, okay, and then use the other identity. Or minus the sign of a minus x, well, because sine is odd, that'd be plus sine of x. So either way, it's going to come out the same. Okay? So, not to worry. There is a checkpoint there, and well worth your effort to do. So I think we're now ready for the product to sum formulas. No, let's see, these are sums of product formulas, okay? Occasionally, when they say that, they really mean very rarely, okay? But occasionally it is useful to reverse the procedure and write the sum of trigonometric functions as a product. This can be accomplished with the sum to product formulas, okay? Now, this is not quite so easy as the others to see, because we really didn't have anything like this before. And I know there must be some place that you would use it. I can't think of where that would be, but it is. So basically what you do, you combine in different ways your sum angle, half the sum angle formulas and stuff like this, and get it to come out this way. Here they've done it for you. All you do is, if you ever need it, you look it up and do it. Okay? That's what you do. This is when you're summing two sines, difference of two sines, sum of two cosines, difference of two cosines. And there's no real pretty pattern here. It just is. Okay? Notice when it's sine, 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 you have sine, cosine, cosine, sine. Okay? When you have cosine, cosine, it's cosine, cosine. When you have cosine minus cosine, it's sine and sine. Okay? So there's no real clear pattern. You just have to just look it up and use it. Okay? Which is exactly what we're going to do for this thing. They do have a little activity on the side, which is a pretty good problem to look at. Why they didn't put it as a problem or example, I don't know. But let's do example 8. See, they don't do example 8, they jump right to application. So let's us do example 8 here. Find the exact value of cosine 195 degrees plus the cosine of 105 degrees. Okay? Now, like I say, very rarely can I think of you ever needing to know that. And if you did need to know the sum of two cosines of different angles, the odds of them coming out to be angles we know exactly their sum and difference of, or half their sum and difference of, that's pretty rare too. So this is really a very specialized example, which I can't imagine when it would ever show up in real life. But let's take our sum of two cosine formulas and see what we do. So let's go back a page. This is the sum. Oh no, it was forward because sum of two cosines. That's this one right here. 2 cosine the sum, half the sum, times cosine half the difference. Okay? Okay. So this will be 2 times cosine 195 degrees plus 105 degrees over 2 times cosine 195 degrees minus 105 degrees over 2. Probably should have put my parentheses there. It makes it look better. Yeah, I think so. Okay. And this will be 2 times, what's the cosine of, what's 105 plus 95? 195 plus 105. 300. Cosine of 300 degrees over 2 times the cosine of, what's the difference of those two? Difference of 195 and 105. 90 degrees over 2. Okay? Which is 2 times cosine of, what's half of 300? 150 degrees times the cosine of 45 degrees. Now we can finally start plugging and chugging. 2 times, okay, cosine of 150 degrees. Where are we, Waldo? Second quadrant. What's cosine in the second quadrant? Negative. So it's going to have a negative sign here. And what's the reference angle for 150 degrees? It's the difference in 180 and 150. 30, we have a good old 30 again. We can't get away from it, can we? What's cosine of 30? Square root of 3 over 2, and it's going to be negative. So this will be negative the square root of 3 over 2 times, what's cosine of 45? Square root of 2 over 2. We knew that one. Okay. Now we can cancel the 2 into one of those, and that will give us minus the square root of 6 over 2. That's what I get, and surprisingly, that's what the book gets to. Right? And then there's a checkpoint, which is the sine of these same two angles, the sum of those sines. Okay? Which will involve using a different one, but very similar context. All right. They also skip example 9. So let's go back. You need this up a little longer? Okay. Let's go back and do example 9. Boy, that sneezing fit has just really clogged my head like crazy. So, sorry about that. Made my nose itch and the company's coming in and everything. Okay, now this example, example 9 on page 386, is one of those that says see larsonprecalculus.com for an interactive version of this type of example. Okay? And here's what the equation is. Solve this equation. sine of 5x plus sine of 3x equal to 0. Okay? Where would you begin? Yeah, let's do that sum to product formula. That looks like the best way to go on this. And the sum to product for sines is that very first one, which is 2 times what? Sine of 5x plus 3x, right? Okay. Over 2 cosine of 5x minus 3x, is that what you said? Over 2. All right, and this is supposedly equal to 0. We've got to find those solutions. So this gives us 2 times, now where did I get the 2? That was from the last problem. Where did that come from? Okay, it didn't come from anywhere, did it? Yeah, oh, it did. I'm sorry, it did. That was part of our thing. I did look back and see that. Okay, all right. So this will be 2 times the sine of not that hard. Say again? 8x over 2, which would be 4x times the cosine of what? Over 2, which is x. Okay. Equals 0. All right. Now we've got, where did the 3 come from? Goodness gracious, things just keep showing up. Okay. All right. 2 times. Now, sine of 4x. Uh-oh. What's that? It's going to involve a double angle formula, which will still require another double angle formula. But let's do them one bite at a time. So what is sine of 4x? That, by the way, is 2 times 2x. Okay, so what's the double angle formula? Remember that one? It's been a long, long time for that one. 2 times what? 2x, yeah. 2x times cosine 2x. Okay? And this is then times cosine x. And that's equal to 0. Now, I think that's right. The sine of a double angle is twice the sine of the x, sine x cosine x. Okay. This is double that. So now we have to do that again. Okay, so that will be a 2 times a 2. And what's sine of 2x then? Two times sine x cosine x. Okay, that's that one. What's cosine 2x? Is it 2? It's cosine squared x sine squared x. Okay, and then all that is times cosine x. Okay. Oh, what a tangled web we weave. All right, let's see what we got now. We've got a 2 times 2 times 2, which I think is 8. Okay? Times. Let's multiply these together and then each of those times that. Okay? So that would be a sine x cosine. This is cosine times cosine is cosine squared times cosine squared is cosine to the 4th x minus sine times sine squared. So that's sine cubed x cosine squared x. Wait a minute. Yeah, I believe that's right. Okay, let's see. Yeah, I think that's right. Now, am I suggesting this is the best way to do this? Not necessarily, okay? Let's see what we can do with this, though. What would be your next step, or a step to do, to try anyway? Big thing in parentheses, what could you do with it? Well, you have some like terms in the two terms, don't you? Let's factor those out. I see a sine x, and I see a cosine squared x. And what's left over? A cosine cubed x, no, it's cosine squared x minus sine squared x. Is that right? And that's equal to 0.
Well, frankly, folks, well, you know, all I did, I factored these two out and left you that, which isn't very helpful. I could have done that up there. I could go back and call that cosine 2x, which, again, is not very helpful.
And again, did I copy down the wrong part? No, I didn't. I copied it down right. Sorry. All this was unnecessary. Hopefully you haven't been writing. I wish I had done better by you. I thought it was going to all pan out to be something easy. It doesn't. It started off not that bad, and I just messed it up. Sorry about this. That's why you really seldom do this anyway. I mean, when will you ever have a problem like that? I don't know. But they had to make up something to give you. Let's just solve that. This says 2 sine 4th x cosine x equals 0. Okay? You can divide out the 2's right there. Done. Okay? And that gives you either sine of 4x equals 0 or cosine x equals 0. Okay? And they don't give you an interval over which to do this, so we're going to have to do a lot of other mess. Okay? Now, do you remember how we did this?
times 4x equals 0? You see where 4x, solve this for 4x, and then we're going to divide by it. So what would 4x need to be to make it equal to 0? Where is sine equals 0? Second? At 0. And pi, 2 pi, 3 pi, 4 pi, 5 pi. All your whole pi's, right? So what we have here is 4x is equal to n pi, right? For any integer n, positive or negative, right? Then divide this by 4, and you have x equal n pi over 4, okay, for any integer x. Whereas cosine equal to 0 for x equal n pi's over 2, because all of your half pi. Oh, that's not quite right. You have to be a little more careful with that, okay? It's pi over 2 plus n pi. That's how you say it. Pi halves plus n pi. Normally you say 2n pi, but they're evenly spaced every pi. Okay? So this is n pi, and that's for any n. Okay? Now, time out a moment here. When n is equal to 2, this is pi halves, right? So this incorporates every one of those. So here's your answer. Now, are they going to just leave it like, oh yeah, no, they do. After a lot of effort and blah, blah, blahs, they finally come up to say, oh, notice the graph that there has x-intercepts occur at multiples of pi force. So yeah, they do get that same answer. Sorry, I got so interested in the double angle formulas and stuff, I was introducing stuff that wasn't necessary. You just solved it as it was. All right, sorry about that. Let's move on to that was our product to sum formula. Now applications. Okay? Ignoring air resistance, the range of a projectile fired at an angle theta with the horizontal and with an initial velocity of v0 feet per second is given by this formula. Okay, they just give it to you. R, which is the range, how far will that projectile go laterally? Okay, not how the distance it goes, but how far it goes laterally. It's 1/16. Now, where did that come from? You probably don't care, but since you're dealing with feet per second, the acceleration due to gravity is 32 feet per second squared. And this looks like half of that right there. That's where the 16 came from. Without giving you any more detail on that, that's where, so it's not just they made it up. That's where 1/16 makes sense. V naught squared, the square of that velocity, times the sine theta cosine theta. That's the formula for it from physics. You can go back and calculate it, derive it if you wanted to, but this is a physics class, so we're not going to. We're going to take their word for it. Where R is the horizontal distance in feet that the projectile travels. Not the total arc length, but just how far it travels this way. If you fire it too far up in the air, it's not going to go very far this way because it goes really high and comes back. If you fire it too narrow, it doesn't have time to get very far. It's not going to go very far either. So the optimum is going to be about 45, we'll see. We'll get there in a minute. Okay, so that's what we have. Okay? Where R is the horizontal distance in feet, V naught is the initial velocity, and theta is the angle of elevation. Okay. Now, first thing it says to do, oh, okay. Okay.
things are a little squirrely here. This slide ended at the end of the projectile travels, okay? The next slide picks up in the next sentence, which is in the same paragraph on that one. A football player can kick a football from ground level with an initial velocity of 80 feet per second. So that's your V0, okay? This is your V0, 80 feet per second. Okay? Rewrite the projectile motion model, which was R is equal to 1 over 16 V naught squared sine theta cosine theta, right? That's what we had on the previous slide and on the page just above this one. In terms of the first power of the sine of multiple angle. So, in other words, we don't want two different functions in here. We want one function sine, but it can be a multiple angle. So, do you remember the identity that looks similar to that? And they suggest multiple angles. And they say sine of a multiple angle. Sine of 2 theta is equal to what? Remember that one? Been a really long time on this one. Like we've already used it today. What would that be? Anybody? What's your double angle formula? Sine of 2 theta is equal to 2 sine theta cosine theta. Okay. Like pulling teeth. Okay. So, here we have our sine theta cosine theta. So if we could multiply by 2, okay, let's put a 2 here, but then we'd also have to divide by 2 too, right? Now this 2 sine theta cosine theta, that would equal sine of 2 theta. So that's going to be at the end here. Okay? And we did that. That left a 32, so it's 1 over 32 V naught squared sine 2 theta. Okay? So basically all this says is go from this to that. If you need a 2 in the numerator, so you have to put a 2 in the denominator. V naught stays the same, and the 2 sine theta cosine theta becomes sine of 2 theta. Okay? So that's rewritten right to the projective motion model in a simple form. That's the simple form. Okay? Now, that's done. At what angle must the player kick the football so it travels 200 feet? Now that means 200 feet down the field. Okay? Now, okay. So that's your R. That's going to be your range. So what we're going to do is say 200, and we'll put the feet in there for now, is equal to 1 over 32. No, we won't. Let's leave the units out because they're not including units in the other things either. 200 is equal to 1 over 32 times V naught squared. That would be 80 feet per second squared. So that would be, I'll just write it as 80 squared times the sine of 2 theta. And they say at what angle, so this is what we're looking for. At what angle? Theta is going to answer that question. Okay? So we got a bit of calculations to deal with. Okay? 200 is equal to Does anyone know what 80 squared is? 6,400 over 32 times the sine of 2 theta. Well, I know that 32 will go into 64 twice, so that's going to be 200 there. And now we got a 200 here and a 200 there. So this is saying 1 is equal to sine of 2 theta. Right? Pardon me? Okay. Okay, thank you. I just can't believe walking into a class that's in progress. I don't know. Okay. So there's their equation right there. Can we solve that? Where is, at what angle 2 theta is the sine equal to 1? Where is sine equal 1? No cosine is 0 at 1. Say again? Pi halves. So 2 theta must be pi halves. Now, you could say others are, 5 halves pi, any 2 pi multiple of that, but, this football player is going to be kicking it, in some other quadrant than the first quadrant. I don't think so. Nick Saban does not want him kicking it back this way at all. He's fired, okay? Or he doesn't want it kicking it into the ground with a negative. No, none of those. I think we'll all be in the first quadrant, don't you? Okay, so let's just leave it at pi halves. So what is theta going to have to be? What is theta going to have to be? How do you solve for theta? Divide by 2. So that is going to be pi fourths. Yes, okay? And frankly, that's going to be his maximum range. Angle that thing 45 degrees above the ground, okay? Hit it midway. That's going to give the maximum range. Time out a moment here. What is 200 feet? About 67 yards. Not quite, but close. 67 yard field goal? Nick's going to sign this guy up. I think so, yeah. Now, that's not quite fair because this is from kicking it to where it lands. That's 65 yards, 67 yards down the field. It lands. It's got to cost the crossbars. So that's going to be considerably shorter than that. But still, it sounds like he's got a pretty good leg on it. And the one picture they show here is a professional. I think he's used to be the Los Angeles Rams, or the St. Louis Rams, or some sort of Rams now. Did one of them move to Phoenix? I don't know. Wherever it was the Rams. Or it could be, now that I look at it, it could be University of Michigan. They have the helmets that look like that too. I don't know. But anyway, probably a pretty good kicker. Okay. So 45 degrees down the field. And the checkpoint there, I already gave it away because I said in example 10, for what angle is that horizontal distance a maximum? I just told you that is at 45 degrees. So does that mean the kickers always should kick 45 degrees? No, because sometimes those guys come in and block it, okay? So especially for extra points and stuff, kick it up higher so they can't block it, and you're still going to have plenty of range to get over it because you're only 3 yards back then plus the 10 of the yeah. So they don't always want to go for maximum range. They sometimes want to kick it really high to minimize the chance of blocking. That's why the really long field goals are more easily blocked, okay? Because they're having to aim lower than a smaller angle. Let's just put it that way. All right, enough of that. Let's go to vocabulary in 5.5. Did I already give y'all the test? I did, didn't I? Okay. All right. Fill in the blanks to complete the trigonometric formula. Sine of 2u is? Excellent. Okay, we've just done it a couple times today. How about cosine 2u? That's certainly one of them. There are two others. You can look those up if you want them. What is sine u times cosine u? That's a product to sum type thing, and that will be that, what is it, 1/2 or 2? I don't even remember. I always have to go back and look it up. That's at the top of page 385, 1/2 of yes, okay, right. And then number 4, 1 minus cosine 2u over 1 plus cosine 2u. Frankly, that sounds to me like that's got to be a tangent, doesn't it? Is it? Yep. That's tangent squared. Let's see if we got it right. Yeah. Tangent squared from page 383. Tangent squared u. All right, number 5.
Plus or minus square root of 1 minus cosine u over 2.
Excellent. Okay, and number 6, cosine u minus cosine v. That's the
Negative 2 sine of u plus v over 2 times sine of u minus v over 2.
yes. I always have those right at the tip of my tongue. Yeah. Yeah. Okay. All right, homework exercises. Any of the odds, 7 through 13, they all have answers in the back. They are worked out at calcchat.com, and number 9 is worked out in fuller detail at calcview.com. Then do any of the odds 15 to 19. They're all at the back of the book, answers in the back, and they're worked out at calcchat.com. Then do any of either 21 or 23. They're both answers in the back of the book and worked out at calcchat.com. 21 is worked out fuller at calcview.com. Do number 25. I think that's sort of a fun problem. Fun according to who you are. But anyway, that would be, I'm going to have to sneeze again. I'm so sorry. We did something like that in class. I think it's with sine. Thank you. All right, reducing powers. Do any of the odds 27 to 33. They're all in the back of the book and at Calc Chat. 27 is at Calc View. Do any of the odds 35 to 39. They're all in the back of the book and at Calc Chat. 37 is at Calc View. Do either 41 or 43. They're both answers in the back of the book. They're worked out at Calc Chat. 41 is at Calc View. Do either 45 or 47. Both are at Calc Chat. 45 is at Calc View. Either 49 or 51. Both at Calc Chat. 49 is at Calc View, but either 53 or 55. They're both at Calc Chat. 53 is at Calc View. Do either 57 or 59. They're both at Calc Chat. Neither are at Calc View. Either 61 or 63. Both at Calc Chat. 63 is at Calc View. Either 65, any of the odds 65 to 69. They're all at Calc Chat. 65 is at Calc View. Do number 71. It's a fun problem. Or you can do 73 if you prefer that. Okay? The picture for 71 is just one of the coolest ever. You know what that is illustrating? That picture at the bottom of page 389, it was at the beginning of the thing too. That is a jet plane breaking the sound barrier. Okay? If you think about it, sound is a compressive wave and it only travels at a certain fixed speed. Jet planes can go faster than this now. And the number of times faster is called the Mach number, okay? And this plane is just breaking Mach 1, okay? Which means as it's traveling, the sound waves are moving ahead of it at the speed of sound. But as the plane approaches the speed of sound, which it can surpass, those sound waves are bunching up in front of it until when it exceeds it, it actually goes through that. And there's a big sonic boom then as it breaks the sound wave. Well, those sound waves are also going to coagulate, you might say, bunch together little water droplets in front of it, which forms that little cloud, and when it breaks the sound barrier, it goes through that. Now, if there's no moisture in the air, you don't see it. But when there is a little bit of moisture in the air, those cloud droplets get compressed there in front of it, and it breaks through, makes a sonic boom, which probably sends that cloud going, and that's a cool picture to catch it just as it's doing that. All right, so either 71 or 73. There is 75 is a true false, which is good to see and understand why. 77 talks about complementary angles, and that finishes the chapter. There's a chapter summary here with all of your equations written, or most of them written down, your identities and all that kind of stuff in 5.1, 5.2, 5.3. What did you learn? 5.4 and 5.5. If you need some more review exercises, 1 or 3 would be good to do. 5 would be good to do. Any of the odds 7 through 15 would be good to do. And by the way, all these odds are at calcchat.com. There aren't any calc views back here. Number 17 is another good one you could do. That's all from 5.1. From 5.2, any of the odds 19 to 25. Okay, from 5.3, any of the odds 27 to 31, any of the odds 33 to 41, and either 43 or 45 or both. From 5.4, 47 or 49 or both, 51, any of the odds either 53 or 55 or both, 57 or 59 or both, and 61. From 5.5 to 63, if you need to, 65, 67, 69, either 71 or 73 or both, 75, 77, and 79. Then they have some more, 2 true false, 81 or 83. Think about it, 85. And then there's a chapter test. Now, the one main difference with the chapter test, all the answers are in the back, but still only the odd numbers are at Calc Chat. But you could do any of those problems 1 through 4, any of 5 through 10, 11 and or 12, any of the ones 13 to 16, and any of the ones 17 to 21. There are some proofs here on the sum and difference formulas and the double angle formulas, power reducing formulas, and some of the product formulas. And then there's some additional problem solving if you are really into it. And you can do any of those. I haven't checked recently, I don't remember if any of these, I think these are in the back too, probably the odds there too. All right, we are ready for, oh, no, we're not, are we? Sorry, we just ran out of time. In fact, we went a little over, but guess what? There'll be no extra charge. Oh, I forgot to do this for you. I forgot to show you, I did the work. Here is that example 10 solution here. Use the double angle formula to get that. We did, okay? And that produced this. And then we applied it here and put R equal 200, 80 equal to V naught squared. Solve that, and you divide both sides by 200. You get 1 equals sine 2 theta. 2 theta must be pi halves. And divide that by 2, and you get pi fourths. Okay? Player must get the football at an angle of 45 degrees, so it'll travel 200 feet, and that's the maximum he can get. All right. Good deal. Work on your test. Y'all all here to hear. There is no class Thursday. Right. Okay. Honors and Awards Day. You're encouraged to go to that. It's over on the Birmingham West Campus in the gymnasium, Arthur Shores Fine Arts Building, which is the gym. And that's where it'll be. And it'll be a nice little ceremony. Any of you receiving awards that you know of? You are. Fantastic. Good. So you'll be there, right? So come and support Daniel too. I've got to be there too. So I'll be there. All right. Good deal. Okay. Why is this? Oh. Say again?